We need to add the details, or at least brief details, about the orbital forcing, which was responsible for those past climate variabilities we saw in the observations or paleo proxies from ice cores and so on. We will see more of them as we go on with the course. Orbital parameters are basically the obliquity, so it is the tilt with respect to the plane of the ecliptic on which Earth rotates around the Sun, and precession, which has two components, one where Earth itself wobbles like a top, but the orbit itself precesses, or the equinoxes get pulled around, or the times of the year where equinoxes and solstices happen get pulled around unless we adjust the calendar. So that happens because of gravitational pull for the other planets around us, Venus, Jupiter, Saturn, and so on. Okay. Ellipticity is also the same reason that it changes, becomes less circular or more circular. Very tiny percent, I think about 2% or so. That impact is not that great, but one thing to remember is that when the obliquity changes, total energy received doesn't change, but the distribution seasonally changes. So you can increase the seasonal contrast between hemispheres when you increase or decrease the tilt or the angle at which the Earth's rotation axis points to the Sun. Okay, so these time scales are very easily calculated, as we know from Milankovich's work, and they are the triggers that are now very firmly established to be very closely related to ice ages and deglaciations. In the current configuration, we have equinoxes on 21st September and 21st March, where Sun is on the equator and the length of day and night are the same at all latitudes. And the solstices, winter and summer, happen on December 21st and June 21, so we just passed that. The Earth comes closest to the Sun around 3rd January in the current configuration, the perihelion, and during the summer on 4th July it actually is the farthest point right now. So obviously in the northern hemisphere we are further during the summer than in the winter, so the summer is tiny bit milder and winter is tiny bit milder because of these small changes. That's what matters, the distribution. So the seasonality on Earth obviously is critically related to this tilt. If it was not tilted, then all latitudes would have the same radiation all through the year. Okay, but because it is pointing away from the Sun during the winter, pointing towards the Sun during the summer, we get a strong season, especially at higher latitudes, where the angle increases. The tropics obviously feel similar amounts of energy throughout the year. So here is the shift of the perihelion, and you can see the animation here. The entire orbit gets thrown around so that the distance from the Sun where equinoxes and solstices happen will change over time. And you can see that here it's called apsidal precession, or precession of the ellipse. So let's start somewhere here in the today we are at December 21 and June 21. In 5,750 years from now, they would have moved to flipped to September 22 and March 20 here, and December 21 and June 21 is where equinoxes would occur, and so on. So 11,500, 16,725 years. So these are accurately calculable because of Milankovitch formulations. Okay, so in 23,000 years we will return to the modern position of March and June, and so on. Okay, these are the kind of amplitudes of the cycles. You can see the ellipticity cycle is here, the obliquity cycle is here, and the precession cycle is here. So the ellipticity cycle is not so great, but it modulates the precession cycle, and together they produce this rich spectrum of time scales. So you can see that the signal amplitude has got combinations of 100,000 and 23,000, 41,000 and 23,000, and all three of them together. So you can imagine now why the paleoclimate record we saw has so many time scales in it. Okay, so depends on where the continents are as well, because all the continents have been moving and they still continue to move. India, for example, pushes into Asia, raises the Himalayas. All continents are moving north. Australia especially moving north at about 3 centimeters per year. At some point few million years ago it used to be clearly way further south, and the equatorial route between Indian Ocean and the Pacific Ocean were open, which had serious impacts on climate as well. Okay, so before we go on, I'll just show this one, energy flux in the current configuration for December, January, February, and June, July, August. What is shown here is the outgoing long wave, which is almost constant everywhere, and in fact has a local dip here because the deep convection and rising air and cloud tops get cold. So the outgoing long wave, which is directly proportional to the emission temperature, is actually lower here in the tropics and higher in the subtropics, and drops off because of cold temperatures at high latitudes. And the two curves here are dotted curve is absorbed, so this is the incident solar flux. Obviously depends on which hemisphere you are in, so you are going from pole to pole, and the northern pole in the boreal winter has no radiation beyond certain latitudes, and in the summer months it will be light 24 hours for several months. But the absorbed radiation obviously is much different. You can see the energy deficit we talked about and the energy surplus that we talked about. Okay, so those are the, and obviously there is a strong seasonal change as well. So we will stop this here to make sure you understand the simple orbital forcings. What happens is not so much the energy change that is critical, but the feedbacks they introduce because of the orbital changes. Okay, I mentioned 65 north before. If you change radiation at 65 north, it typically tends to control the melt of the glaciers at the end of the summer. So if snow, for example, doesn't melt by the end of the summer, then fall winter months get colder, more snow falls, so you have snow accumulation and glacier growth. Of course also sea ice is affected, but if the radiation increases at 65 north, which is a critical latitude, then you can initiate the melt at the end of the summer and go into a deglaciation. Okay, so it's those ice albedo feedbacks and various other feedbacks like vegetation feedbacks and so on that determine the actual outcome in terms of glaciation and deglaciation. Okay, that's critical to remember. At weather time scale, I mentioned, within a day you can have changes because of faster feedbacks like evaporation and precipitation, clouds, winds, etc. But even on these long orbital time scales, ice albedo feedbacks are the most critical ones. We'll see that the slow ocean circulation is also a player at some intermediate time scale.